So what I'm talking about today is Wireshark at enterprise scale. So the question is, the first question you might ask is, do enterprises use open source software like Wireshark? And of course, the answer is yes, absolutely they do. I think maybe 20 years ago, people were a bit more hesitant about embracing open source, but these days it's absolutely a very common tool that everybody uses. So the real question then becomes, well, what's different about how Wireshark gets used in enterprises? What are some of the challenges that they have in scale? And scale is really the key. So what we'll talk a little bit about is why we capture. When I say we, I mean enterprises. So why do enterprise companies capture packets? What's in it for them? How do they do the capture? And then how do they deal with some of those problems of scale? So different enterprise organizations are arranged differently. The names of the different groups may vary, so different terminology. So DevOps might be production, or it might be operations. There's generally a networking team, so network operations, and a security team. And these are all groups of people within enterprises who have some interest in packet capture, at least potentially. So let's think about it from their point of view. Why are they capturing packets and what's in it for them? So when you think about DevOps or the application team, they're the people who own all the applications. And they might be internal applications, they might be customer-facing external applications. They're responsible for application delivery and performance, and these are really business critical functions. So they might be losing millions of dollars if those services go down. Now, generally, because they're running applications and services, they own those services, they may have developed them, and they have access to all of those server applications and logs. So their troubleshooting process tends to be log focused. That's where they'll start from. They may, in some cases, request packets if they're trying to troubleshoot an advanced problem, but more likely they'll maybe finger pointing. It might be our application is having problems. We think it's a network problem. Prove that it isn't. And they generally don't have access to the networking equipment themselves. Again, it does vary by enterprise, but in a lot of cases, they have to request assistance from the networking team if they want to set up a packet tap or if they want to access packets. So the networking team, obviously they own the network, so they configure it, they build it, they run it. They're responsible for the network availability and performance, and they tend to have a fairly high level view of network operations. So they rely on statistics, information from their network management system that's fed from their routers and switches, firewalls, and other active elements in the network. And in some cases, they may have NetFlow IP fix, so flow level generators and collectors feeding fairly high level dashboard systems. They generally, because they run the network, they can easily set up captures, so they can easily set up taps on the network, repatch things as needed. But they'll usually look at their high-level tools first when they're trying to troubleshoot a problem and rely on packets only for advanced troubleshooting. When they really have a problem, okay, we're going to have to go and look at the packets. That's when they'll go and do that. And then finally, we've got the security team. So they're responsible for the security of the enterprise. So like the applications team, it's mission critical. Many organizations have a lot of critical IP that they want to secure. And the security team frequently has their own network monitoring equipment. So security covers a lot of areas, including endpoint security and so on, but there is a significant network element to it. So the way that budgets are allocated between the different groups can vary quite a bit, but frequently they will have their own networking equipment. So they're looking for intrusions, indications of compromise, threats, and so on. They may be scanning for vulnerabilities in the network. In some cases, they may have limited access to the physical network, so they may still rely on the networking team for actually setting things up. So if they want to install a new appliance in a data center, if they want to get IPs allocated, if they want to set up a new tap, they want to change some firewalling rules, sometimes they don't have direct access for that. Their tools tend to need full packet capture, so they're doing deep packet inspection, so signature analysis and so on. And they are interested in packet capture frequently for evidentiary reasons, right? So they want to look at the packets to understand in detail what's been happening and retain that for incident analysis. So although they don't necessarily own the network and may not run it, they have a strong interest in being able to tap the network. So what can't you do without packets? So we've heard that some of these teams will treat packets as a last resort, but there are a lot of problems that you can really only solve if you have the access to the packets on the network. So the obvious one is collecting evidence, right? So if you're investigating security incidences, being able to look at the specific traffic on the network, where it came from, where it went to, what was transferred, is fairly important. You also need access to the packets if you are developing new signatures, for example. So if you are testing rules for your firewalls or looking for zero-day exploits and you're developing new rules, then having access to the packets is very important. As well as, of course, on the networking side of things, debugging network transport layer issues, so TCP, tuning, all of those kinds of things, protocol application errors and so on. And finally, regulatory compliance can come into it. So we're starting to see in the financial industries, there are regulations requiring financial companies to maintain records of their network activity. So the regulators want to know, when did a particular trading company learn about a stock price change, for example, and when exactly did they issue buy or sell orders, things like that. Also starting to see some of that in health as well. So there are regulatory requirements around packet capture and so on, network security. So when you think about what is different about enterprise compared to what you might do as a hobbyist or as an individual, and the key problem is really scale. So enterprise networks are just a lot bigger and more complex. They tend to be multiple capture points. The links are a lot higher speed. So rather than gigabit, you're talking about 10, 40, 100 gigabit. Huge data volumes are being transferred. You would like to store history. So you'd like to be able to capture and be able to look back in time, but there's a cost trade-off for that. So the more history you want to store about your network, the more it's going to cost you. And finally, having collected vast amounts of information, you need to be able to comprehend it. So you need to be able to visualize it. You have to have some way of searching it, which is going to rely on indexes. Otherwise, it's just terabytes and terabytes of PCAP files, and you can't do anything with it. And quite a few of the talks at SharkFest are people looking at how do you break up large trace files and process them. So how can you automate that to make it easier? Okay, so we talked a little bit about why enterprises capture, and we'll talk a little bit next about what are the techniques and what are the approaches and strategies for that. So I've kind of broken this down into a bit of a continuum. On the left, in the kind of smaller scale, less sophisticated, is on-demand capture, moving through live inspection, triggered recording, and continuous recording. And this tends to be sort of the different types of strategies used by organizations of different sizes. So have a look at those a little bit individually. So when you think about on-demand capture, what you might picture is the one IT guy in the company with a laptop and a patch cable, right? And he's running around the building, plugging his laptop into different points in the network, trying to debug network issues. It's frequently a single guy or a single consultant. So they might not even have IT staff who are network savvy, and they have to bring somebody in to solve the networking issues. The advantages of this, it's low to no equipment costs. You can do your capture on a laptop, just with Wireshark, for example. It's all existing equipment. It is very high in time cost, so there's an opportunity cost to having your IT staff running around trying to solve networking problems or security issues. Or you're hiring in consultants, which you're paying by the hour, so that can be quite expensive too. And it tends to be very reactive, so it's ad hoc or on demand. So you only do it when there's a problem. You go and start looking to see if you can see what the issue is and address it. So it's very much temporary and it's very much iterative. I plug into the network over here, I have a look around, I can't find what's going on, so I'm going to go and try somewhere else, so I'm going to try a different filter and so on. As an organization grows and gets a little bit more sophisticated in terms of its networking and its investment into that, the next step tends to be live inspection. So the idea there is you're actually going to do continuous capture of packets on your network, but you're not actually going to record it. So you're just doing live inspection of the traffic. So the types of examples of these tools are IDS systems like Surcada and Snort, or flow analysis tools like Zeek. There are also commercial alternatives to that, so intrusion detection systems, network behavioral anomaly detection, network detection response. There's a whole slew of AI-based products that are getting a lot of hype in the market. The key point is that it has permanent dedicated equipment. So you normally have at least one rack at this point. You have some networking gear, some switches, and you're going to have a dedicated piece of equipment to do that. And where you're placing that in the network will depend on what sort of coverage you have. You may only have one office, you may only have one rack of equipment. And most of these tools are alert generators. So they're generating some sort of summary information, some logs or some alerts. The logs, the alerts themselves or the logs are stored over a long period of time, but the packets themselves are not written to disk. In the case of intrusion detection systems, where they're signature-based, the matching on a specific packet, they'll often log the particular packet that caused the alert, but they generally will not record the entire flow, like the entire session. They don't provide context. So the next step up from there is triggered recording. So a lot of these security appliances, particularly commercial ones, will advertise some sort of smart recording or intelligent recording. And what they'll do is when they trigger an alert, rather than logging just a single packet that caused the alert, they'll attempt to record the entire flow. So the advantage of this compared to continuous capture is you're going to use less disk space. But of course, as with any signature-based system, you have to determine what the triggers are going to be in advance, right? So this doesn't work against zero-day threats because you don't have a signature that matches that flow yet. And they also have to choose what context to provide. So if an IDS system triggers on a particular packet, it might record that flow, but it might not get the DNS lookups that were done related to that flow earlier, for example, or it might not associate that with a net scan that occurred earlier in time. Another problem is they tend to have a limited ability to go back in time. So they might have a small buffer in memory. So if the fifth packet in a flow is the one that triggered your IDS rule, they might be able to go back in time and record from the first packet. But if it's half an hour or an hour into the session before the alert gets triggered, then they may not have enough history to actually go back to the beginning of that session to get the whole context. And then finally, in kind of the larger scale, is continuous recording. So this is where you have your capture system installed in one or more points within the network, and they're recording capturing all of the packets on the links and recording them all to disk in a rotating file store. Optionally, they can do that with filtering, or they can just capture literally everything. And generally, there's some form of compression in order to maximize disk space. We'll talk a bit about that later. The advantage of recording all of the traffic all of the time is that you don't have to risk missing the context or the important information. Obviously, how much storage capacity you have will limit how long of a history you can actually keep. And that time limit is the amount of time that you have to investigate an incident that occurs before that data then gets overwritten by new captured data. So ideally, in an enterprise, you're going to want at least several days of storage so that if something occurs on a weekend or overnight, then by the time you get into the office on Monday, security team is operating again, perhaps, you can still look into that. And ideally, you're going to have a week or more of storage. In some cases, people will be looking for months or even longer. These continuous recording is generally complementary to live inspection tools. So if you're doing this, you're also doing intrusion detection systems and other live analysis tools. And they may even be hosted on the same hardware. So it may be the same appliance that can actually do both. Okay, so let's think a little bit about how we do the packet capture in terms of the technology. So acquiring packets, where we put the taps and the tools, what kind of storage requirements we actually have based on our time that we want to have in history, encryption and decryption issues, and compression. So first of all, on-demand capture, going back to the simple form again, is very straightforward. You can capture on an endpoint, although don't let Jasper hear you say that because he'll be very angry. Don't capture on the endpoints, it's a bad idea, but you can, but don't. For lots of reasons, and there are great talks in SharkFest about exactly why you shouldn't do this. Main reasons are NIC offloads. So what you capture, when you're capturing on an endpoint that's communicating as part of a conversation, what you will see is not exactly what's on the wire because of accelerations in the network cards. Also, timestamp quality tends to be quite poor, and the very fact that you're capturing on that system is going to affect its performance. So if you're trying to debug a performance issue and then you do packet capture on the machine that's having a performance problem, you're only going to make it worse. The better way of doing things is with port mirrors or a span on your switch if you have support for that, and then a laptop. Now, a lot of this laptop does actually have an Ethernet port, but a lot of new laptops don't have physical Ethernet ports anymore for doing packet capture on. But the good news is that you can use a Thunderbolt or USB network adapter. You can even get 10 gigabit ones. So if you have a laptop with a NVMe SSD drive and you have a Thunderbolt adapter, you can tap even fiber 10 gigabit network links for a relatively limited amount of time, but probably more data than what you want to look at in Wireshark anyway. So this is a good way of doing it. There's also portable sniffer systems. So some of the SharkFest sponsors are people who build small packet capture devices that are portable. Again, often they will connect to a laptop with USB or something like that. Again, pretty much on demand, so ad hoc capture. When you move into live and continuous capture, you want some dedicated hardware for doing that. Again, you can use port mirrors and spans, but that does tend to use extra switch ports on your switches, so you have to have a bit of a trade-off there. And when you have more than one tool that wants to see the same data, if you're using span ports on switches, you need separate switch ports for every tool. And you need to, your switch then needs to duplicate the traffic across all of those tools. So again, you're using up ports. Alternatively, you can use taps. So passive or an active tap. Passive taps are used optically, where you're just tapping off some of the signal. Active taps are used for electrical Ethernet. The passive ones tend to be a single direction, so a fiber, so you use a pair of them to get both directions of a link. Nice thing about taps is they maintain all of the timing details, so they're literally looking at the same signal. But if you're using fiber taps, be aware of the link loss when you insert a tap. So you need to check the optical budgets to make sure that you're not taking too much of the signal away. The next step up from that, if you like, is network packet brokers. This is sometimes referred to as tap aggregation or tap ag. And again, some of the SharkFest sponsors are companies who make packet brokers. They're generally multi-port devices that look a lot like a switch, may have similar hardware. You can use them to tap multiple links at once. They frequently have their own timestamping engines. And so they will timestamp the packets on the ingress ports. And they often have capabilities for doing filtering and truncation, and in some cases even decryption. So they can do man-in-the-middle style decryption. And then they can duplicate traffic out to multiple tools. They can aggregate multiple slow links onto a higher speed link. So if your packet capture system can do 40 gigabits and you're monitoring a large number of 1 gigabit links, you can aggregate those together with tags on the packet so you know which port is which. You can as I said, you have multiple tools, and you can also load balance. So if, for example, you're doing packet capture, and you want to have a longer retention time, you can load balance incoming traffic across multiple appliances. So here's a relatively old-fashioned diagram of a network. And there's lots of things in here that you can pick up which are kind of not super up to date. So we've got things like trusted Wi-Fi. So we have a trusted core zone, a DMZ, telecommuters, which these days we would probably call working from home. In some cases, that's the entire company, including the CEO. Business partners these days may include things which are hosted in cloud. But the reason this is an old kind of diagram is, if I can grab a pen, the idea of this was that you had a relatively limited border. So if you want to tap the network, if you tap that point, then frequently that's the one place you need to look at in your network, right? So the threat model is that the bad guys are on the internet, everybody on the inside is trusted, everyone is good. There's no way for bad stuff to get into the network except through that one connection. And even if you have branch offices, frequently the branch offices were only connected to the internet via head office, right? So they'd have a leased line or a VPN back to the central office. But today we have bring your own devices, we have zero trust networking. And the assumption is that you can't trust any of the devices in your network. You can't trust the LAN ports that are in your office and your cubicles. You can't trust the laptop from the guy from accounting who might click on a phishing email, and so on. So the whole idea of zero trust networking is to segment the network into different areas. The ink, okay. And so the threat models have changed, right? So the threats can come from anywhere. And so you need a lot more visibility into the network. So there are good arguments for being able to tap multiple points within your network, including branch offices, which now are generally split mode tunnels. So they'll have local internet access. So the bad guys can get in from the internet there. And as we said, the guy in accounting with a laptop, he takes it home and clicks on a malware link and brings it into the office, plugs it in, connects to the Wi-Fi. So you really want to be able to look at multiple points within the network. Now, in this diagram, that's kind of shown as multiple probes. In a real enterprise network, it's more likely to be tap points. So each one of these points is somewhere that you want to have connected to a packet broker. And then you're going to use the packet broker to select which ports to look at or which locations you need to look at in the network. And even things like in the DMZ there, we can see a firewall. There's a probe that's monitoring multiple ports on it. And that can be very useful because you can then look at how your firewalls are actually behaving. Are they dropping the packets that they're supposed to drop? And is there anything getting through that maybe there shouldn't be? So it can actually be very useful as a way of validating that your not only firewalls, but other types of middleware are actually working the way that they're supposed to, and you haven't had configuration issues, for example. Okay. So continuous capture. You might look at that and think, well, this is going to use way too much disk space. I can't really afford to do that. So let's figure it out. And this is a calculation that's very useful to do, and a lot of people haven't seen it before. If you think about a 1 gigabit per second link, right, it's very common. A 1 gigabit link, if it's fully saturated, is doing 125 megabytes of data per second, which is 450 gigabytes in an hour. It's about 10.8, so call it 11 terabytes per day, 75 terabytes a week. And that's just the packets, right? So any indexes, any metadata, flow information, and so on is going to be on top of that. And worse news is that network links are bidirectional. So if it's a gigi link and it's fully saturated in both directions, it's 151.2 terabytes every week. If it was 10 gigabits, then obviously it's 10 times higher, so you're 1.5 petabytes a week. So these sound like very big numbers, right? You can buy hard disks, they're up to about maybe 20 terabytes in size. SSDs go up to maybe 30 terabytes in size if you're willing to pay for them. So this is something that's not going to fit on a single disk. This is quite a lot of data, and we're only talking about a 1 gigabit link, potentially, right? So they're quite big numbers. So is this idea of trying to store a week's worth of data at a time actually something that's practical? So this is an example of the REENZ network in New Zealand, which is a research and education network in New Zealand. It's like our version of the internet too. And this is a particular link. It's a 10 gig link. It's a wide area. So it's a connection between New Zealand and Australia, which is our nearest neighbor. And there's a couple of things when you look at this data, and this is from about a year ago, I think. So the graph on the left side is 1 day, and then the graph on the right-hand side is a week. And there's two things that kind of jump out at you straight away. First of all, the green line or the green bars are the traffic from Australia to New Zealand, and the blue is the traffic in the other direction. And you immediately see that there's a lot more data in one direction than the other. So in this case, New Zealand is a consumer of data overall compared to Australia. So there's a lot more data coming into New Zealand over that link than is leaving. So first of all, it means that the link is not saturated in both directions. It tends to be this asymmetry between the two. And if you are a hosting provider, for example, you're a content provider, then it's going to be the other way around. You're going to have a lot more outgoing than you do have incoming because it's only ACKs, right? And requests for things. When you look at it over a week, you can also see that there's, or a day, you can see that there's a strong diurnal variation, right? So the day to night cycle, when people are at work, they are doing a lot of things during the day. During the night, there's a lot less traffic, but there's still some because there's a lot of automated processes, there's a lot of background transfers, caches are being filled, all that kind of thing. So a couple of points. When you look at this graph, it looks reasonably high resolution, but each one of these points is still like 5 minutes long. So the numbers that we're looking at are average over a 5-minute period. So this link will definitely be spiking to 10 gigabits. It'll be saturating for periods of maybe a few seconds at a time. But over 5 minutes, the average is only 2 to 3 gigabits, right? And when you look at the whole week and average it out, there's only 2.8 gigabits of traffic on average in the sum of both directions over that whole week. And when you add it up, it's 212 terabytes. It's the total amount of data transferred over that link in the sum of both directions. So rather than saying, oh, this is, you know, what do we say in the previous slide? We said 151 terabytes a week for a 1 gigabit link and 1.5 petabytes a week for a 10 gig link. Well, here's a 10 gig link, but it's only doing 200 terabytes, right? So the total utilization is actually a lot less than you might predict. But if you're a wide area networking guy and you're looking at this and saying, hey, this thing's hitting 30% average load during peak time, you may well be looking at provisioning a higher speed link. And I think actually since these were taken a year or so ago, I think these links have already been upgraded in terms of the bandwidth. Because if you're hitting 3 gigabits, 30-40% load over a 5-minute average, it means you're probably pegging for several seconds at a time and your TCP connections are suffering. So you don't want the utilization to be that high. Okay, so another advantage when trying to capture a lot of traffic to disk is compression. And it turns out that some network data compresses really well. So things that are plain text or HTML or plain text JSON compress very well. And the compression ratios can be better than 2 to 1. Sometimes it can be as high as 5 to 1. And then some of the data is incompressible. So if somebody's streaming Netflix work really hard to compress that as well as they can. So you're not going to be able to compress it anymore when you're doing a packet trace. And the same thing is true for encrypted data. If encrypted data was compressible, it would mean that there's information available there. So when data is encrypted, it usually looks completely like noise. It's completely random. There's nothing visible in it. So you don't really want that. So between these two types of data, if it's incompressible, right, if it's Netflix, then I don't want to record all the Netflix packets to disk. That's just a waste of my disk space, particularly when it's lots of copies of people watching the same thing. I might still want the packet headers so that I can do flow analysis on them. I can still look at the timestamps on the packets and the TCP flags and so on. But I don't need the actual contents. And the same thing is true for encrypted data. Once I know that it's encrypted, maybe there's some TLS information that I want to pull out from the handshake at the start of the connection. But after that, the rest of it is, unless you have the encryption keys, there's no point recording it. So you can just truncate those packets. So I mentioned entropy is one way of determining whether something is encrypted or not. So there's kind of two approaches. One of them is doing protocol analysis in real time, so deep packet inspection, looking for TLS handshakes. And the other way to do it is just to look at the contents of the packets themselves. So it's completely stateless. And the Shannon entropy is a number between 0 and 8. It's measured in bits. And you can distinguish between packet payloads without knowing anything about the protocol stack. So you literally don't have to know whether it's HTTP or what it is, but by looking at these figures, it gives you a general idea for what kind of traffic it is. Is it text, which is quite compressible, and we want to keep it because it may have something interesting in it. JPEG is kind of in the middle. Binary compressed data tends to be over 7, and encrypted data is often 7.8 to 8. So incompressible payloads, as we said, if they don't have useful information in them, and that does vary a little bit by user, you can just truncate them. And what you are not truncating is the data that does compress well. So you combine those two things together and you can often get anywhere between 4:1 and 10:1 compression. So if we think about our REANS data, probably a lot of that data will have been encrypted. So we could be truncating those packets. And if we do that, then with 4:1 or 10:1 compression, we're down to 20 to 50 terabytes per week for that 10 gig link. And I can buy a 20 terabyte hard drive. Now that 20 terabyte hard drive might not have enough performance to keep up with recording that data, but there is enough storage capacity there to hold a week's worth of data. So the costs are not necessarily as high as you would expect. Finally, encryption and decryption. As we said earlier, if data is encrypted and you don't have the keys, then there's really no point capturing the packets beyond the headers because you're not going to be able to do anything interesting with it. It used to be that if you had the key pair for a web server, for example, you could just use that key to go back and decrypt all the data. But with more recent TLS versions, perfect forward secrecy, you can no longer do that. So even if you have the server keys, the private key for a web server, you still can't actually use that to go back and decrypt previous sessions. So you can do some client-side logging, but that's only going to be for clients that you control and you've set up logging of those events, logging of those secrets for that particular session. And then finally, there's the kind of man in the middle approach, where you have some sort of TLS proxy that does re-signing of sessions. And again, there are other talks in SharkFest that go into encryption in more detail. And crypto offload is also common in server farms. So if you have a multi-tier web application, you've got some web servers, frequently your cloud provider will be doing TLS termination for you. So by the time the packets arrive at your web server, it looks like HTTP, not HTTPS. So that's all offloaded into hardware. So in that case, you can actually see the unencrypted information, and it might be worth capturing that. Okay, so let's think a little bit about how we do scaling. So how do enterprises deal with the sizes of their networks? One of the problems is really thinking about how do you understand the volume of data that we're talking about. Even if I can get a whole week's worth of data and crunch it down into 20 terabytes of packets, what do I do with 20 terabytes of packets? You can't open that in Wireshark, right? So we'll talk a little bit about fabrics, about capture metadata, time synchronization, and visualization and search tools. So first of all, the idea of fabrics is that if you have a large network, you're typically talking about multiple data centers, multiple offices, hundreds or thousands of staff, and tens of thousands or even hundreds of thousands of devices, which means that your packet capture infrastructure is also going to be very large. You may have tens to hundreds of packet brokers and capture devices in a large organization. And you might think that sounds like a lot. We have several customers with over 100 physical packet capture devices in their networks. So it really does scale to that kind of size. So Fabric is a distributed way of managing all of those things. You don't want to be logging into 100 different devices, whether they're packet brokers or capture devices, to manage them. You also don't want to be centrally storing all of your packets, right? Because you'd be almost duplicating the amount of load on your network. You really want to store the packets as close to where they were captured as possible. But you do want some kind of centralized tools for doing your visualization. So here's kind of a deployment diagram. We're using Endace terminology here, if you like, but it's generally similar for other solutions as well. And you can think of this as single Endace probes might be edge devices, so branch offices, things like that. In a large data center, you might use a stack of probes in order to increase your retention time. So you're not necessarily doing it for performance, although you might need that, but by stacking up multiple probes, I can increase the total amount of storage. On the left-hand side, you've got a central management tool. So there are things that you want to manage, like configuration management, fabric health management, so checking that all of your systems are operating correctly and they're not dropping packets. You can also deal with upgrade orchestration and licensing and things like that. And then at the top, we have investigation managers. So this is kind of our, the search head, if you like. So this is where your analysts, security guys, networking guys will log into a box to get an interface that they can use to investigate issues. And one of the really important things about this diagram, I think, is what's not on the slide. So what's missing? So what's not on here is flow collectors. There's no flow collectors and there's no database. There's no database cluster. And the reason, again, is that you want this to be a scale-out solution, right? So you want your data to be distributed. And each of these probes, as well as capturing the packets and storing them, is also doing DPI. It's doing flow analysis. But rather than streaming all of that back to some huge central database cluster that you have to manage, it stores all of that locally on the box and provides, it does all of the indexing locally and all of the roll-ups and provides APIs for you then to go and search them remotely. So every time you start a new data center, deploy a new probe, as well as adding storage and capture ports, you're also adding database capacity and you're adding more compute. So that sort of scales in a very natural kind of way. Multi-point capture. So there's what are the advantages to having multiple points of capture within an enterprise? Obviously, the first one is just coverage, right? So the more points that I'm monitoring traffic in my enterprise, the more likely it is that when there is an incident, I will have captured packets that are relevant to it because I'm looking in multiple places. The second one is history. So by storing that history, it means that when there's an incident, as well as trying to find the evidence of what's going on, what the problem is, I can also go back in time and say, well, how was that application behaving when it was working normally? So being able to do that kind of baselining can be really useful. There's a few things that you can really only do when you have multiple capture points. Part of it is reachability. So when you think about investigating a network issue, so a client-server application, you've got a problem, you even have a packet trace. So what's the first question you always ask about the packet trace is, where was it captured? Was it captured near the client or was it captured near the server? All right, so if I'm sending a SYN from a client to a server and I don't get a response, it could be because the SYN didn't make it to the server or the SYN ACK didn't get back from the server, or it could be that the server itself didn't respond. And if you want to determine, is this a network issue or is this an application issue, then you really need captures at both ends. So I need a capture near the server to tell whether or not my SYN arrived. I need capture near the client to see whether the ACK came back. Maybe it's an issue with the client. Latency is also something that you can measure with multiple points. So if you have a single packet capture point, you can measure round trip latencies, but not one-way delays. So if you have streaming media, for example, you're getting buffering problems, you're getting latency bursts, being able to track individual packets through multiple points in a network, different sides of firewalls and routers and so on, you can actually see where latency gets introduced. You can't do that if you only have a single measurement point. And finally, mutation. So when I send a packet to a server, I expect it to arrive at the server as I sent it. But in some cases, there's middleware boxes in your network which are making changes to your packets. And they might be stripping out headers, they might be modifying different things. And having capture points near both the client and the server lets you see whether or not what you sent is what actually arrives at the other end or not, whether something is interfering with that. Another important another important approach when doing capture at multiple points is you don't just need the packets, but you need some metadata about the packets too. So the packets will tell us what happened. So there are very good evidence of what literally happened on the wire. But we also need to know things like when it happened. So obviously a packet trace is going to have timestamps, but if you don't know whether the clocks were synchronized, then you don't know whether you can trust the timestamps. If you can't trust them, you can't compare them to other points in the network, you can't correlate them with logs. You also want to know where the packets were captured from. As we said, it's important to know whether it was near the client or the server. So if you're just capturing packets to files on your laptop with, cryptic file names, when you come back in 3 months' time, you're not going to know, why did I capture these packets? What are they about? You may also want to collect information about how you captured the packet. So what were the versions of the tools and so on. And there may be contextual information as well, like IDS alerts, trouble tickets that were created, things like that. The one issue with metadata is if you're sharing that data with others, you may need to anonymize that. So you may need to strip it back out. So if you're using Trace Wrangler, for example, Trace Wrangler is an anonymization tool, which only anonymizes things that it knows about. So if it doesn't understand a protocol, it removes it. So in the case of this metadata, if Trace Wrangler doesn't know about it, it'll just remove it. So clock synchronization. If you have a very high resolution clock, that's fine for a single point capture, and it will let you measure round trip time very accurately. And you can also use it if you're near the server to measure service response times. But if you're capturing at multiple points, the clocks need to be synchronized, as mentioned. And in the financial industry, there are regulatory requirements starting to come in around this as well. So in Europe, MiFID II regulations say that not only do you have to capture all of your trades, for example, your feed information, but you have to show that you can timestamp that to within 1 microsecond. So it's industry specific, but it's starting to become more common. Finally, you need some way to visualize the information. There's no point having terabytes and terabytes of packet traces if you can't actually understand what's happening. So you need to look at information over time, connectivity, flows and applications. And these types of visualizations don't rely on packets directly. They're usually based on some sort of flow information or indexes, which can be used to accelerate searches. So I'm not going to dwell on the screenshots because I'm going to hopefully do a demo. We have time at the end. So talking about finding things in terabytes of packets, you need to have indexes. So you need time indexes. How you're looking for things will influence what kinds of indexes you need, but often you're starting from an IP address, so a address of interest. It may be a 5 tuple if it's come from an intrusion detection system, so it knows the ports and the time when something occurred. You want to be able to extract those packets in order to download and dissect them. But indexes can be very large. So if you have comprehensive flow indexes, they can be a significant fraction of the original packet storage in size. And then finally, you also want some sort of APIs so that you can do automated mining of information. So REST APIs, SIEM integrations, for example. So when an alert is triggered by my IDS, it goes to my SIEM wants to be then able to reach into the packet storage system and do a automated mine to collect those packets, read them out, store them somewhere else, for example. Again, I'll skip these screenshots and I will see if we can do a quick demo. Always fun. So again, this is Indace equipment. This is a investigation manager from the diagram that we're looking at before. It's a head end. This is a demo in our Austin lab, which is our partner integration lab. So what we'll do is we'll log in as if we're an analyst and we're investigating issues in the network. Hopefully this is going to work. Yep, okay. So when you're logging in, what you'll typically see is the list of previous investigations that you've created. This is a demo server, so there are some old investigations there. We'll just create a new one. And this particular investigation manager has a number of different physical probes attached to it. There's 3 or 4 different physical probes. And so the first thing we need to do is give it a name. So I'll call it SharkFest. Is the size okay? Looks right. Yeah. And then we need to select some data sources. We need to tell it which probes we're interested in looking at data from and which resources. So there's a couple of tags in here. This is probably a little bit small. Blow it up. There's a few tags that are predefined. So there's a tag for all sources, archives, which are information that has been recorded and then kept aside. Rotation files are the continuously rolling information. And then there are user-defined tags as well. So in this case, these are by models of equipment, but it could also be by region, by city, data center, purpose, like web servers or whatever. So we're going to select a few sources here. The ones that we want, main ones. So I think there's 3 here, 3 probes. We need to select a time range. So by default, it's the last 5 minutes. Apply that. And we select some tools to have a look at. So let's have a look at some conversations. We'll do some traffic breakdowns. And we'll have a look at the bandwidth as well. And so what's happening here is the investigation manager, as we said, doesn't receive flow records constantly. Instead, it's just sitting there. It's a very lightweight VM. And when you request a visualization, it's doing database queries out to the individual probes, collecting all the information back, sorting it if necessary, aggregating it, and displaying it. So these 3 probes in total are doing 3 to 4 gigabits of capture over that last 5-minute period. And we can do a breakdown, for example, by data source. That'll tell us which of those packets were arriving at each of the probes. So there's our 3 different probes, DP4, 6, and 7, and DP9, 1. And we can immediately see that the DP9, so the 9000 series machine, is seeing a lot more traffic, like 10 times as much. We can also disable display of traffic within one particular visualization, just to hide it. It doesn't affect the other ones. We're not actually doing filtering. We're just changing the aggregation on that display. And then maybe for this one, we want to look at application breakdown. And so what it's doing there is looking at all of the flows across all of the sources, and then aggregating those across the sources that we've selected, plotting them over time. And then finally, there's the actual individual flows or conversations. These are IP conversations, IP level conversations, where we can look at individual TCP and UDP flows as well. Now, there's a bunch of other tools. I haven't gone through all the different ones available. Frequently, there's enough information here to solve network level problems by looking at TCP flags, for example, zero window indications, all of those kinds of simple things, spikes in SYN activity, and so on. But what you would typically do with this is you have some external information from an alert or a problem that you're seeing, and you're going to use this interface to drill down and develop filters and then pick up exactly what you want. So you might end up with just a few flows, and then on any individual flow, you can download it to your laptop as a PCAP file, for example. You can archive it on the investigation manager, so you can refer to it later, even if the rolling storage would have otherwise overwritten it. You can launch Wireshark on the investigation manager itself, and you can extract files if it's, say, an HTTP session, for example. As well as doing that on individual sessions, you can also do it on all of the data. So if we look here, you can see that there's probably 100 gigabytes or so worth of data here. But what we can do is we can just say, I can download it, but I don't really want to download 100 gig of stuff to my laptop, particularly over a VPN. So what I'll do is I'll launch Wireshark. So what the investigation manager is doing is starting a container, running a copy of Wireshark in it, and then simultaneously it's sending queries out to the 3 probes that are connected, requesting the packets that match the time time period that we were looking for. It's collecting all of those back to the investigation manager, sorting them by time, and then pushing them into Wireshark. And it's already there. So that was pretty quick. So there's a couple of interesting things here. This is just Wireshark. I think in this version it's 3.6. There'll be newer versions coming out as the tools get upgraded. And you can literally do anything in here that you can do in normal Wireshark. So for example, we can look at the statistics, we can do protocol hierarchies, all of the typical tools that you can do in Wireshark. And if you've been to SharkFest in the past, you may have logged into one of these devices and used some of these tools in Wireshark for some of the packet challenges in the past. This is just the latest version. So a couple of things of interest. One of them is that we've only got 136,000 packets. And if I've got hundreds of gigs of traffic, I would expect to see a lot more than 100,000 packets. So what it's actually done is instead of giving us 100 gig, it's just given us the first 100 megabytes. And that avoids then overloading Wireshark. So rather than seeing the whole 5 minutes, if we look at the capture statistics, file properties, find it, there we go. We can see how much time range we actually got. And there you go, the elapsed time was less than 1 second. So over a 5-minute period, the first 100 megabytes was less than 1 second. And if we then wanted to see more of it, there's a button up the top here, which will load the next 100 megabytes. So we can apply filters, we can then page through the traffic, block at a time, entirely within the probe without having to download anything to your laptop and process large trace files. One new thing that you can do in this version is you can now filter packets within Wireshark and then save that. So you can do an export packets into whatever format you like. And then you can download that from the investigation manager. You can also use the file extraction tools that are part of Wireshark as well. So any of those kinds of things, you can extract all that information and then download it later. Okay, oh, well, the other thing I was going to mention was very briefly, if we look at the statistics again, Wireshark these days supports packet traces with more than one interface in it. So if you remember in our vision investigation, there were 3 different probes. And if we scroll down, we can see that this trace file has 3 different interfaces in it, which are named using these strange numbers, which are tags. So the unique tags associated with each probe, which then lets us tell on every packet which of those 3 probes did it actually come from. And you can see this in the frame level information. If you look here, you can see the interface ID. And we can add that as a column, for example, in Wireshark. Now we have the interface ID, so we can tell which of those probes the packets were captured on. You can Because it's a Wireshark field, you can filter on it, so you can look at just one at a time. You can use that for comparing client versus server, for example. So that's a very brief overview of what that kind of head end can look like. Okay, so decided to stop running. Let's go to here. Okay. So in conclusion, Wireshark is used in enterprises to a very large degree. And the kinds of problems that enterprises have are mostly to do with scale. So Wireshark is a fantastic magnifying glass. It's a great tool for looking at detail. So we heard from Gerald this morning, it's now up to 2,800 protocols and over 200,000 unique fields. So it's fantastic. For enterprises to make better use of it, though, they need tools to wrap around it to help manage the scale and the complexity of enterprise networks. So high performance capture at multiple points, all of the overhead of managing and maintaining those systems, generating and collecting all the metadata associated with those capture points, indexing and storing the packets and managing the rotating file sets, and doing that distributed search across the fabric. So putting those two things together works really well. So thank you very much. Please fill in your session feedback survey. Now it turns out that if you're in the Zoom session, the feedback survey is attached to the Zoom session, from what I understand. If you are here in person and you want to do that, the links for those I think are going to get sent out by email later. So if you have made any notes, you want to give us some feedback about the talk, please do that. You can also find me at the Endace table, or you can contact me on Discord also if you're on Zoom. Okay, do we have any questions? Oh, there's Q&A. Yeah. What types of enterprises have this many taps all over? I can barely get one large data set. It does vary enormously. And so as we were saying kind of earlier, one of the interesting things that you find talking to large enterprises is that the different groups within an enterprise have their own budgets. And sometimes the network capture equipment is owned by the security team, and sometimes it's owned by the networking team. So depending on who has budget will vary a lot in terms of how things are actually deployed. Types of enterprises that will install a lot of probes and a lot of taps are ones that take network security very seriously, right? So either they have a regulatory requirement or they have some intellectual property, which is very important to them. They really want to keep that secure. Or they have a network which is business critical, right? So they're someone like you know, a web store. If the web store goes down, they don't make any money, or a service provider. So that tends to be the motivating factors for why you might do that and why you might have very large deployed networks. Oh, yeah, okay. Do you want to read it? Okay, so the question was, in case you didn't hear it, have you ever seen distributed taps used at large schools or universities? So the first question, do schools and universities use Wireshark? The answer is absolutely yes, they do. Like any other kinds of enterprises, it's a great tool, and being open source, it's also readily available. Do we see large distributed taps at universities? Frequently, universities have very large on-campus networks. So they have multiple data centers, and they will sometimes have packet broker infrastructure available so that they can monitor different points in the network at will. But often they are not flush with cash perhaps, so they're not necessarily going to have a large number of monitoring appliances. That makes sense. Thank you. Okay, well, if you don't have any other questions, I will release you all early so you can get into the coffee. And thanks for coming by.